So okay, so in the last class we solved one problem, right? Finding the LEB of the set. So quickly we solve that problem, and then we start the sequences. So what the set we take? A equal to set of all 1 minus 1 by n square such that n in n. So this is our set. We have to prove the LEB of the set A is 1. Okay, that is our aim. So clearly 1 minus 1 by n square is always less than or equal to 1 because we are subtracting some quantity from 1, therefore it's always less than or equal to 1. Okay, therefore this is true for every n in n. So since this is true for every element of A, therefore 1 is an upper bound. 1 is an upper bound of A. Now we have to prove that 1 is the least upper bound. So for that, suppose if I remove some quantity, then that number will not be a upper bound. Suppose if we take R, if we take some other upper bound B, suppose if we take some other upper, suppose B is an upper bound of A. Suppose we take some other upper bound. Now we have to show that 1 is the least. That is what we have to prove. To prove 1 is less than or equal to B. That is our aim. Suppose not. Suppose B is less than 1. Then what will happen? Suppose B is less than 1. We get some contradiction. Suppose B is strictly less than 1. Then actually what is it? This is 0 to 1. Suppose B is here because B is less than 1. So every element B is positive and less than 1. Therefore this B is of the 1 minus some positive quantity. Because it's always less than 1. So therefore it should be 1 minus epsilon. So suppose if you take some other element, this C here, this should be 1 plus some number. Okay. So anyway, we can write any number. We can write, suppose if we take less than 1, that B can be written as 1 minus some epsilon. If we take outside after 1, we can write 1 plus epsilon. We can add positive number, we will get a bigger element. If you subtract some number, we will get a smaller element. Therefore, this B can be written as 1 minus epsilon for some positive epsilon. For some epsilon positive. Okay. Now, what we have to prove, we have to find an element here from A. So we have to find X from A, which is bigger than A, less than 1. So what is the element X? Okay, that is, so we have to find the element from this. So that is 1 minus some m square in A such that B is less than 1 minus 1 by m square. You have to find such an element, is exist or not. So B is nothing but 1 minus epsilon. So work backward. So that is we have to find 1 minus epsilon is less than 1 minus 1 by m square. We can cancel 1. If you multiply minus, we will get a epsilon greater than or equal to 1 by m square. Okay, that's inequality changes. If you multiply minus, or strictly less than, strictly greater. So epsilon is greater than 1 by m square. Now, so this always we can find m is a natural number, right? Because m is a natural number, therefore m square is also a natural number. So we can find, so just cross multiply, we get m square times epsilon is strictly greater than 1. Okay, so we get a natural number. So such an m exists by Archimedean property because choose. So since epsilon is positive, now apply Archimedean property to this number and 1. So because when we have a two real number and one real number is positive, we can apply arithmetic property, right? So whenever two real number x comma y in R with one real number is positive, then we can find that there exists a natural number n in n such that n into x is greater than y. So this is arithmetic property. Now we are going to take x equal to epsilon because this is positive and take y equal to 1. Now applying Archimedes property, these two numbers, we get there exists a natural number m in n such that m into epsilon is greater than 1. Okay, so therefore we can take m square also. M square also natural number, right? So otherwise, what is the relation between this m and m square? So by Archimedes property, we get a m. So we know that m is smaller than m square, smaller than or equal to m square, because if we take m equal to 1, we get same thing. Okay, so therefore if you divide it by this, cross multiply this, we get this thing, right? So anyway, such an number exists by Archimedes property. So by Archimedes property, this is holds, and we can say that this m square is epsilon is always, because m square is bigger than epsilon. Sorry, m square is bigger than m, right? Now multiply epsilon both sides. Therefore, m square epsilon greater than m into epsilon. But n into epsilon by Archimedes property, we know that is greater than 1. Therefore, by transitivity, we get m square epsilon is greater than 1. Therefore, we get this one. So from this, we get this one. Just to multiply 1 by m square both sides, we get this one. Now multiply minus, you get this one, and then add 1, you get this one. Therefore, this is nothing but b. So we get a reverse back. Now once you find how such an m exists, then you can take the reverse. So we will get. So we can find the element from A which is bigger than B. Therefore, we can find the element x or 1, that x is of the form 1 minus 1 by m square between B and 1. So which is a contradiction, because B is an upper bound. That means what? Every element of A should less than or equal to B. But now we find an element from A which is bigger than B, which is a contradiction to the B is an upper bound. Therefore, our assumption is wrong. What is our assumption? B is less than 1 is our assumption. So this is wrong. So 1 should be less than or equal to B. Therefore, 1 is an least upper bound. Okay, any doubt in this? So main thing is we have to use Archimedean property. So existence of natural number guarantee that this guarantee Archimedean property. Okay, now we start sequences. So sequence is nothing but it's just a function from natural number to real number. If you suppose if you want to real sequence, the codomain is R. Suppose if you want any sequence, then codomain you have to change accordingly. Okay, so now definition for sequence. Definition: a real sequence, because in the real analysis we discuss about real sequence only. So a real sequence is a real sequence is a function. A sequence is a function. A real sequence is a function f from natural number to R. Suppose if you want to complex sequences, then it's a function from n to complex number. In general, if you have a sequence in x is any non-empty set, then the codomain should be x. Domain always natural number, but the codomain is depending upon what the sequence you need. If you need a real sequence, you have to take the codomain is R. If you want a complex sequence, you take the codomain is complex number. Okay, so a real sequence is a function from natural number to R, and usually we denote. So that means what? Every element in the domain we have to assign. So 1 is an element of natural number, we have to assign some element here, right? So we call that element is f of 1. So image of 1. So if we take 2 in the domain, so if 2 maps somewhere, we call f of 2, and so on. So we call that f of n. In general, any n, we call this is xn. So just notation. So we let xn is nothing but image of n, and this xn is called the nth term of the sequence, and call the xn is called xn the nth term of the sequence, nth term of the sequence. So usually we denote the notation, this sequence denote xn, or sometimes use the notation x1 comma x2 comma x3 and so on. So we can represent sequence either this notation or this notation. So at least sequence is nothing but we have to arrange the image of numbers of natural number. That is, first you have to, so f is a function from natural number to r. So we have to take the image of the element 1, and then you take the image of the element 2, and then you take next you have to take the image of 3 and so on, and then the image of the nth element and so on. So this is a sequence. You can represent sequence like this. So you have to put the bracket. So we denote this as xn. So therefore in general what is xn is the nth term, that is the image of n under the function f. So this is a sequence. So if you take any function, suppose example, suppose I am taking the function g from natural number to r defined by g of n equal to, suppose I am defining n plus 1. N goes to n plus 1. That means what? 1 goes to 2, 2 goes to 3, 3 goes to 4 and so on. Now what is the sequences? So first you got to take the g of 1 and then g of 2 and so on. So this sequence is nothing but what is g of 1? 2. What is g of 2? 3, 4, 5 and so on. So this is sequences. If given any sequence, say that this is the image of the corresponding element. For example, suppose I am given the sequence like 5, 8, 9, 10 and so on. Suppose I am saying these are sequences, therefore this f of 1 should be 5. 1 maps to 5, and then 2 maps to 8, 3 maps to 9 and so on. So given any sequence, we can say what is the image of the corresponding element. Okay, so these sequences. Okay, now we discuss some examples of more sequences. So this is just a function. We have to assign some real numbers to all natural numbers, that is sequences. So example 1, suppose if you fix, so usually, so this is a natural number. So for simplicity, I am writing this is a natural number, this is a real number. So suppose I fix some constant c, then every element maps to c. This is a one function. Everything maps to a single element, that is a constant function. So that is, we take that xn equal to c for all n. So that is everything maps to the fixed number. So first we fix some constant c in R, then everything maps to c. That is xn we denote. Xn is nothing but the n f of n. F of n nothing but xn. So everything maps to for n in n. Okay. So this sequence is called constant sequences, because we have a constant function. The corresponding sequence is called constant sequence. So what is the first term? C. What is the second term of the sequence? C. Third term is C, and so on. So these are constant sequences. Okay. C, C, C is a constant sequence. Now, the second example. So suppose I am defining function n from n to r defined by f of n equal to 1 by n, because n is a natural number, therefore start from 1 to 3, right? Now 1 maps to 1 by 2, 1 maps to 1, 2 maps to 1 by 2, 3 maps to 1 by 3. Therefore the xn is nothing but 1 by n. So that means what? In general, f of n maps to 1 by n for all n. So these are sequences. So what is the first term? 1. What is the second term? 1 by 2. What is the third term? 1 by 3 and so on. The nth term is 1 by n and so on. So this is sequences. It's very important sequence. The third example, suppose I'm taking xn equal to minus 1 power n plus 1 by n. So that means what is the first term of the sequence? If substitute n equal to 1, we get to 1. If substitute n equal to 2 plus 1 is 3, therefore minus 1 by 2. Alternative plus and minus. Substitute 3, we get 3. Substitute 4, we get minus 1 by 4, and so on. So these are these sequences. Yeah, that is what is the function? F of n equal to minus 1 power n plus 1 by n. So this is a function. The next sequence is minus 1 power n. Xn equal to minus 1 power n. So that is what is the image of 1 is minus 1. What is the image of 2? 1. What is the image of 3? Minus 1. Plus 1, minus 1, and so on. So that is f of n is minus 1 power n. That means what? 1 maps to minus 1, 2 maps to plus 1, 3 maps to minus 1, alternative minus plus 1. So this is a function. This is one of the sequence. So therefore, any function from natural number to R is a sequence. Okay. So another, suppose I define the identity function, that is n goes to n. So therefore, the sequence xn is nothing but just n. So what is the image of 1? 1. What is the image of 2? 2, 3, 4, and so on. So this is a sequence. This is one of the example. And 6. Suppose if you take xn equal to 2 power n. So that means what? What is the image of 1 is 2. 2 power 1. What is the image of 2? 2 power 2, that is 4. What is the image of 3? 2 power 3 is 8. Therefore, this is 2, 4, 8, and so on, 16, and so on. So this is a sequence. And then if you take 1 by 2 power n, xn equal to 1 by 2 power n. So what is the images? The image of 1 is 1 by 2. The image of 2 is 1 by 4, 1 by 8, 1 by 16, and so on. So this is another sequence. So we can define the sequence using the recurrence relation. So that is, suppose we have a first few terms of the sequence. Suppose x1 is 1. Suppose I am defining the first term is 1, second term is 1. Now I am defining the nth term is sum of previous two terms, that is xn minus 1 plus xn minus 2 for n greater than or equal to 3. Because already I defined x1, x2. For x3 we have to sum. Therefore, what is the first element is 1. Image of 1 is 1. Image of 2 also 1. What is the image of 3? Just the sum of previous two terms, that is 2. And then x, the image of 4 is nothing but sum of these two is 3. And then sum of this is 5. So this is actually Fibonacci sequence. Okay. So 1, 1, 2, 5, 8, and so on, 8, and then 13, and so on. So we can define sequence like this. Okay, this is a recurrence relation. And this sequence is called Fibonacci sequence. Fibonacci, writing double C. Fibonacci sequence. So now one more, we can take some complicated sequence. Suppose the nth term, that is the n maps to 2n plus 1 by n square minus 3. So anyway, the denominator is not 0. So when the denominator will get this 0, n should be root 3, but root 3 is not a natural number. Now what is the first term? N equal to 1. So therefore, what is f of 1? The numerator we get 3, the denominator we get minus 2. Therefore, minus 3 by 2. Because minus 3 by 2 is a real number, right? Okay. Now what is the image of 2? So nothing but 5 by 2 square is 4 minus 1 is 5. So the second term is 5. Now the third term is, you can easily find 7 by 6. Image of 3 is 6, 7 by 6, and so on. So this is another differences. Even we can take some other form. Suppose I am taking first term x1 is 0.3, only 1 3, and I define x2 is 0.33, and so on. In general, the xn I am defining 0.n times 3, 3, 3, 3, 3. How many times? N times. This is also sequence. We got to assign every element of domain, there is some element in the codon. So these are all examples of sequences. Okay. Now, when we say a sequence is converges, important thing, definition, a sequence is said to be converges or converges sequence. So let xn be a real sequence. Let xn be a real sequence. Okay, we say that the sequence xn converges. Converges to some real number, converges to some x, but x is a real number. So when we say a sequence converges to the real number x, if you take any epsilon greater than 0, that is for given epsilon greater than 0, for given epsilon greater than 0, there exists a natural number, there exists n, capital N in n, such that for any k, for all k which is bigger than or equal to this capital N, we have the distance between the sequences, and then we have otherwise we can say this xk belongs to x minus epsilon to x plus epsilon, or we can say the distance between xn minus x is strictly less than epsilon for every n greater than or equal to, or you can take k, every k greater than or equal to this capital N. So this is the definition, and then we can write the number x is called the limit of the sequence. So the x is called limit of a sequence, limit of the sequence xn. Okay, and then we write xn converges to x, we write this notation xn approaches to x as n goes to infinity. As n goes to infinity, then xn approaches to 0. Or we can write limit n goes to infinity, the xn value is x. Either we can use this or this. Okay, suppose a sequence is said to be divergent if it is not convergent. We say that a sequence, divergent sequence, we say that a sequence xn is divergent if it is not convergent. Divergent if it is not convergent. Okay, so that is the definition of convergence. So that means what? When we say we have sequence x1, x2, etc., xn. Suppose we have sequence x1, x2, and so on, xn, and so on. So we say this sequence is converges to some real number x. That means what? We have a real line 0 something. Okay, suppose we have a real number x. So suppose we assume that x is here. So we have to mark this x1, x2, etc., xn. Suppose maybe x1 is here, x1 is somewhere, x1 is here, x2 is here, okay, x3 may be here, x4 may be here, and the x5 may be here, and the x6 may be here. Anyway, so when we say this sequence converges to x after certain stage, so maybe this stage, maybe this is xn, maybe this is some xk or something. So after some stage, all the sequence numbers are very near to this x. So that is, so I give that this is a, okay, anyway. So this is a center x, suppose given epsilon. Suppose if you want to the distance between the point x and the sequence is epsilon, accordingly we can choose the stage. Okay, so suppose I'm considering this open interval. This point is x minus epsilon. This point is this endpoint is x plus epsilon. So after certain stage, all the sequence numbers are lies in this interval. That this has happened, then we say xn converges to x. Okay, suppose if we give some other epsilon, suppose maybe give some other epsilon 1, then we can find some other stage, maybe the small one or bigger one. Then you'll get some other stage such that after certain stage, all the sequence numbers are lies in this interval. Okay, so this stage depends upon this epsilon. So how many distance you want from the point x and then sequence member, then accordingly we can choose the stage. So this is called the stage. The definition, so we say there exists n. So this n is called actually stage of the sequence. So after the stage, all the xk's are belongs to the interval. Or simply saying the distance between the point x and then the sequence are very small. That is less than epsilon for any k which is greater than or equal to n. So n is the stage. This capital N is the stage. So this n depends epsilon. If you give some other epsilon, we can choose some other epsilon. If no such x exists, then we say the sequence is a divergent sequence. So for example, so any doubt in this for convergent sequence? So convergent when we say a sequence convergent, there is a real number x such that xn converges to x. That is another definition. So we say a sequence is convergent sequence. So we say xn is convergent. When we say a sequence is convergent, if there is a real number x in R such that xn converges to x. So convergence means what? Definitely it converges to some real point, real number x, and any sequence converges to exactly one point. So suppose a sequence converges 2 points, the 2 points should be equal. Okay, so this is a very important thing. Okay, now we discuss some examples, or we got to write a mathematical definition of using quantifier. You have to write the definition of when we say a sequence is convergent. Okay, xn is convergent. So the sequence xn is convergent if first we need there is a real number x in R such that xn converges to x. But what is the definition of xn converges to x? For every epsilon greater than 0, there is a stage n naught in n such that the distance between xn minus x is less than epsilon whenever n greater than or equal to n naught. So we have tried this one. So for every epsilon greater than 0, open, there is a stage, and I call n naught in n such that, so for any k greater than or equal to this n naught, such that all xk's are belongs to the open interval x minus epsilon to x plus epsilon. How many bracket we opened? 4. Therefore we have to close 4 brackets. Why we need this layer by layer definition? We can easily write the negation. So what is the negation of, yeah, so what is the negation of x is divergent. Okay, convergent negation is divergent. So xn is divergent. What is the definition? So divergent if, what is the negation of for there exists for every. So we have to negate layer by layer for every x in R. So what is the negation of for every? There is some m. You can take epsilon or m. Okay, that is not issue. So there exists a epsilon greater than 0. If we take any stage for any n naught in n, but here don't, this is actually condition. Okay, so if you take any n naught, if you take any k, for any k greater than or equal to that particular n naught, x k does not belongs to x minus epsilon to x plus epsilon. So this is a negation of xn is convergent. Okay, now we find a limit of constant sequence. So we, first example, suppose if we take constant sequence, it is convergent. So the first one is xn is constant c for every n in n. Now what is the sequence? So we claim that xn converges to c as n goes to infinity. If n increases, this xn converges to c. So that means what we have to prove? Given any epsilon, we have to find a stage such that after certain stage, all the sequence numbers are very close to c. But everything, all the numbers of xn's also c. Therefore, so given epsilon greater than 0. So you can change from the first stage itself. So this is a real number c. So what is the sequence? X1 is c, x2 also c, x3 also c, everything c. Therefore, from the first stage onwards, everything very close to c. So choose or take that stage n naught is 1 from the first stage itself. Everything close to the modulus of xn minus c. Actually, modulus of xn minus c is nothing but modulus of c minus c. So c minus c is 0. 0 is less than epsilon. We know that because epsilon is positive. Okay. So given any epsilon, I can choose the stage is 1. After this stage 1, everything very close to 1. That is the distance between xn and c is less than epsilon. Therefore, xn converges to c. If xn is a constant sequence, every constant sequence converges to that constant. Here stage is 1. Okay. So finding the stage in the sequence is very important. Now look at the second example. We take the sequences xn is 1 by n. So just to mark it the sequence. So this is 0 and 1. So if substitute x equal to 1, we get this is x1. If substitute n equal to 2, we get x2. x2 is 1 by 2. So this is actually x2. Substitute n equal to 3, x3 we get 1 by 3. 1 by 3 somewhere here. And x4 is here. So if everything, so but everything is positive number. Because natural number is a positive number. Therefore, all the xn's are positive. Therefore, these numbers are converges to 0. So we guess that this xn sequence converges to 0. So if you take x5, x5 may be here. If you take x6, x should be here, so on and so on. Therefore, everything very close to 0, but no xn's comes this side. So that means what? This side, if it comes this side, means xn is negative, but each xn's are positive. So therefore, all the xn's are positive, and this approaches to 0 as n approaches to infinity. Now we guess that xn approaches to 0, but we have to prove that xn converges to 0. How to prove this one? So we found that limit is 0. So what we have to prove? To prove given any epsilon, what we have to prove? Given any epsilon, we have to find a stage. There is n naught in n such that for every n greater than or equal to n naught, the distance between xn and 0 should be less than epsilon. So that is we got to prove. Okay. Now we start with the arbitrary epsilon. We have to find the stage. So let the epsilon is positive. Now our aim is to find a n naught such that if you take any n greater than n naught, the distance between xn minus 0 is less than epsilon. Suppose assume that such an n exists, and then we have to find. So what we have to prove? Modulus of what is xn? Xn is nothing but 1 by n minus 0 is less than epsilon. So that is modulus of 1 by n is less than epsilon. So modulus is because all the 1 by n's are positive, therefore this is nothing but 1 by n is less than epsilon. So that is what we need. 1 is less than n into epsilon. So already we know that by Archimedes property, now this is work backward. So we did this for your work backward, we need this. So if you get this, you will get this. If you get this, you will get this one. Therefore, finally you get this one. Therefore, we did the proof. So how we'll get this one is guarantee that Archimedes property. So since epsilon is positive, by Archimedes property, there is a natural number n or some n naught in n such that n naught into epsilon is bigger than 1. It takes another real number is 1. So I take this is x and this is y, apply Archimedes property to this real number, we get some natural number n naught in n such that n naught into epsilon is greater than 1. Now we get this relation only for n naught. So this is our stage. So what we got to prove? If we take any n which is greater than or equal to n naught, what we have to prove? We have to prove the distance between xn and 0 is less than epsilon. Okay. So n is greater than or equal to n naught. So what about if you multiply epsilon both sides, n into epsilon greater than or equal to n naught into epsilon, because epsilon is positive. Okay. So this also greater than 1. Therefore, n into epsilon is also greater than 1. Therefore, epsilon is greater than 1 by n for any n greater than or equal to n naught. So we get a proof. So we get this, therefore we get this, therefore we get this, therefore we get this. Reverse process. So therefore this xn converges to 0. So here the Archimedes property gives the stage. Any doubt in this? Therefore the sequence 1 by n converges to 0. It's very important sequence. Now one more example. So Archimedes property guarantee that there is a stage, existence of stage of a sequence. So if we take third example, suppose if we take xn equal to 1 by 2 power n. Now if you just mark it, substitute what is x1? 1 by 2. So that suppose this is 0 and this is 1. Now what is x1? 1 by 2. So this is x1. What is x2? 1 by 4. So maybe here this is x2. And what is 1 by 3? X3 is 1 by 8 somewhere here. And everything is positive because each xn is positive, therefore its approaches to 0. Okay, we guess that this xn approaches to 0 as n approaches to infinity. Now, but we have to prove that xn converges to 0. That means what given any epsilon greater than 0, we got to find a stage such that modulus of xn minus epsilon is, but here x is 0. So we start with the arbitrary epsilon. So let epsilon greater than 0. So what we have to find? We have to find there is a n naught in n such that we take any n which is bigger than or equal to n naught, the sequence xn minus 0 is less than epsilon. We have to prove. So that is, what is this? Modulus of 1 by 2 power n is less than epsilon. So that is, because 1 by 2 power n is positive, therefore we have to remove the modulus, therefore we get 1 by 2 power n is less than epsilon. So such a n exists or not by Archimedes property. Okay, so that is 1 is less than epsilon times 2 power n. or you can apply log both side. We'll get log of 1 is 0 and this is less than n into epsilon or log epsilon 2 epsilon, that is 2 epsilon power n, but okay, sorry, you can write separately. Anyway, I write here. So by Archimedes property, given epsilon greater than 0, by Archimedes property, there exists a n naught in n such that n naught into epsilon is bigger than, okay, better I am taking this. Instead of, since epsilon is positive, therefore log epsilon is greater than or equal to 0. Otherwise, so otherwise we can go some other way. So simple way. So there is a relation between this 1 by n and n. So anyway, we can go there. So what is the relation between 1 by 2 power n? So n is always smaller than 2 power n. Substitute n equal to 1, 1 is less than 2. Substitute n equal to 2 less than 4. Therefore, this is always true. This is true for every n. Okay. Therefore, 1 by 2 power n is less than 1 by n. By Archimedes property, we know that we can find a natural number n such that 1 by n is less than epsilon. Therefore, we get 1 by 2 power n is less than epsilon. Therefore, we get the proof. So we use the result 1 by n is less than 2 power n. Therefore, from this we get this one. So we know that this is happened. Why? By Archimedes property, we know that 1 is less than n into epsilon. By Archimedes property. So we'll get this one. So therefore, this 1 by n sequence converges to 0. So these are all important sequences. But if you take the sequence n, will not converges. So this xn is n. So this sequence is divergent sequences. Why is divergence? Suppose assume that this is converges. Suppose xn is converges. Convergent. So that means what? There is a real number x such that xn converges to x. So that means what? By the definition, if you take any epsilon greater than 0, there is a stage such that xn minus x is less than epsilon. So in particular, I am taking epsilon equal to 1. This is true for every epsilon. In particular, if you take epsilon equal to 1, then there is a stage n naught in n such that the modulus of xn minus x is less than epsilon. So, but epsilon value is 1. Therefore, modulus of xn minus x is less than 1. Therefore, we can write it as minus 1 strictly less than xn minus x less than 1. Now add x both sides, we get x minus 1 less than xn less than x plus 1. But if you take, so this is true for any n greater than or equal to n naught. So suppose x is here, any real number, x plus 1 is here, we can find a natural number somewhere here. So because we can, given any natural number, any real number, we can always find some natural number here. So in particular, if you take xm, so xm value is m, but m is bigger than x plus 1, but here we know that all the xn's are less than x plus 1, which is a contradiction. Therefore, if you assume this xn is convergent, then we get a contradiction. Therefore, the sequence is divergent sequence. Otherwise, if you mark all the points, so this is x1, that is 1. So this is x2, that is 2, and so on, x3, x4, and so on. So this is an increasing sequence, and this is not bounded above. Therefore, this diverges to infinity. Okay. Now, first you guess the limit. Okay, because in the exam point of view, you no need to prove all the things, but you got to guess the limit. So how to guess the limit? Using the known theorem. So known sequences. So far we know that what are the sequence we know? The 1 by n sequence converges to 0. This sequence we know. And then 1 by 2 power n converges to 0. This also we know. So using the known sequence, we can say the limit of the other sequences. And before that, we have some theorems, that is sum of sequences also converges. Suppose if xn converges to some point x and we have another sequence yn that converges to y, implies that if you subtract and then our addition, that is plus or minus yn, is converges to x plus or minus y. If you take xn plus yn, is converges to x plus y. If you take xn minus yn, is converges to x minus y. And if you take the product xn into yn, this also converges the product of the limit xn into yn. And if you take the quotient xn by yn, provided each yn is non-zero and y is non-zero, it converges to x by y. So provided y is non-zero and then each xn's are non-zero. So quotient of two convergent sequence converges to the quotient limit. Okay. Suppose we multiply some scalar, then c times xn. C is any constant. This converges to c times x for any c. Okay. So these are all algebra of sequences. Now using this, we can say the limit of any sequences. Now we'll discuss some examples. First one, suppose if you take xn equal to 2n plus 1 by n square minus 3. Now what is the limit? So this goes to actually 0. So this approaches to 0. So why this approaches to 0? So from the numerator we can take n outside, we get 2 plus 1 by n. From the denominator we can take n square is outside, therefore we get 1 minus 3 by n square. Okay, now we can cancel 1 n, therefore what we'll get? 2 plus 1 by n into 1 minus 3 by n square. Anyway, if n approaches infinity, this term goes to 0, right? Therefore the numerator is approaches to 0. So 2 plus 1 by n, this is sequence, this approaches to 2 because 1 by n approaches 0. Now the denominator 1 by 3 by n square. So 1 by n converges 0, therefore 1 by n square is also converges 0, therefore 3 by 1 square converges 0, therefore it converges to 1. Now, but we have 1 by n is there, therefore this takes to 0. So otherwise, how to prove this using the definition? We have to prove that the modulus of 2n plus 1 by n square minus 3 minus 0 is less than epsilon for every epsilon greater than 0. So we have to prove this. We have to estimate this. Okay, so we have to use some result. We can easily prove this. So anyway, so this approaches 0 because we have a 1 by n in the denominator. If n approaches 0, this 1 by n takes to 0. That's it. Okay. So if you take some other example, and then I already said that the limit should be unique. Suppose we have a sequence, xn sequence is converges to x, and again the xn is also converges to some other y, then x should be equal to y. So that here any sequence, if it is converges, then it has a unique limit. Okay, it's very important. Now, for examples. Suppose if we take xn equal to 1 by n plus 1. As n goes to infinity, this goes to 0. Right? This is trivial. And the second example, suppose if we take an equal to n plus 1 by 2n plus 3. Now what the sequence converges to? So we can take n outside from the numerator, we get 1 plus 1 by n. The denominator you can take n outside, we get 2 plus 3 by n. Now we can cancel n, so therefore we get 1 plus 1 by n by 2 plus 3 by n. Now as n goes to infinity, this term goes to 0. Again this term goes to 0. Therefore finally we get 1 by 2. So therefore the sequence an converges to 1 by 2 as n goes to infinity. Because 1 by n converges to 0 as n goes to infinity, that's why we get 1 by 2. Now, if you take some other example, an equal to 2 by square root of n. So as n goes to infinity, this approaches to 0. Okay. because 1 by what is the relation between this n is bigger than or equal to square root of n. Okay. And then otherwise we can say that if you take the square root, it's always smaller than it's a very approaches 0. Okay, so therefore this 2 by square root of n approaches to 0. And then if you take some other example, suppose if you take a n equal to square root of n plus 1 minus square root of n. So where this sequence converges. So what we have to do, we have to keep the n's are in the denominator. So if the suppose n's are in the numerator, we try to cancel n's in the numerator. So better what we have to do, we have to multiply and then divide by the same number. So that is we have n square root of n plus 1 minus square root of n is there. So what I am going to do, we have to multiply square root of n plus 1 plus square root of n. So I am going to multiply this term and then divide it by the same term. It will not change, right? Now in the numerator we have is of the form a minus b into a plus b should be a square minus b square. So a square is the root is cancelled, we got n plus 1 minus b square, again root is cancelled, we get n. So divided by square root of n plus 1 minus square root of n. So we can cancel n. We have a 1 by square root of n plus 1 minus square root of n. So clearly as n goes to 0, n goes to infinity, this approaches to 0. Okay, it's clear because 1 by n is approaches to 1 by root n approaches to 0. Approaches to 0. Okay. And there are some theorems are there. Okay. What are the theorems? Suppose xn converges to x, then modulus of xn converges to modulus of x. So that is the first theorem. Suppose if xn converges to x, then modulus of xn converges to modulus of x. But the converse need not be true in general. Okay, suppose modulus of xn converges to modulus of x, but xn need not be converges to x. What is the example? So converse not true. So that is we take xn is minus 1 power n. So that is what is the sequence? Minus 1 plus 1 minus 1 plus 1 and so on. So this sequence is oscillate sequences. So it's never converges. But if you take modulus of xn, is nothing but just to 1. So it's a 1-1 sequence, therefore it converges to 1. So modulus of xn converges to x that is mod x. So mod x here x is nothing but 1. But this xn not converges because it's a oscillate sequences. 1 minus 1, 1 minus 1. It's oscillate sequence, right? Therefore the converse need not be true. When the converse is true, only when the limit is 0. If xn converges to 0, if and only if modulus of xn converges to 0. If the limit is 0, then both the directions are true. Okay, so that is the second theorem. Suppose if xn converges to 0, if and only if modulus of xn converges to 0. Okay, but if you take some other sequence which is converges to a non-zero limit, then if xn converges to x, then mod x converges to mod x, but converges need not be true. The third theorem says equivalently say xn converges to x is same as xn minus x converges to 0. If and only if modulus of xn minus x is converges to 0 by result 2. Okay. Okay, good. Now the theorem. So these are all simple theorems. So in a convergence sequence, the first few terms does not affect any convergence of the sequences. So that is what I'm telling. Suppose we have sequence x1 xn equal to x1 x2 etc xn and so on. Suppose this sequence is converges. Okay, now I define new sequence yn. Okay, so I am just don't bother about the first few terms. Suppose up to xk, I remove these terms. I start from here. Okay, so maybe I start from some xn. It's a new sequence. So that is xn plus 1. I am taking these sequences. So that means what? I remove the first few terms, finite number of terms. Again, the new sequence also converges to x. Okay, so suppose you are adding new terms or you are subtracting few terms, this convergence sequence limit does not change. Okay, suppose you can remove some 100 terms of the sequence, still the sequence converges to x. Suppose otherwise, suppose you are adding some new terms are there. Suppose z1, z2, some z100. Suppose you are include these 100 terms to the sequence, the first few 100 terms are this, then again this sequence is converges to x. So if you in a convergence sequence, if you change anything in the first few terms, the convergence does not change. Okay, that is important. If you do anything, you can omit or you can you can include some new term. Once the sequence converges, you can do anything in the first few terms, finite number of terms. Still the sequence converges. Okay. Now another theorem, or actually this exercise, I can state as a theorem. Suppose we have a convergence sequence. Okay, what is a convergence sequence? Suppose Bn is a convergence sequence, and each Bn's are positive, and Bn converges to 0. And we have another sequence An, which condition that modulus of An minus A is less than or equal to that Bn for all n in n, then the sequence An converges to E. Suppose An minus A is less than epsilon, less than or equal to Bn for any n, but the Bn is converges to 0 sequence and positive. Then this An is converges to A. Yeah, this is very important result. Then another theorem. Suppose we have a sequence xn. It's a sequence, and suppose xn converges to x. Okay, and we know that, and the limit is positive. Okay, then what can you say about the xn's? This xn or the xk's are which is bigger than, then there exists. So there exists n in n such that this xk are bigger than x by 2 for k greater than, for any k greater than or equal to this capital N. Why? Since xn converges to x. Suppose I mark here. So this is a real line. Suppose x is here, and it is given that x is positive. Therefore, 0 is somewhere here. Since xn converges to x, by definition, after certain stage, everything near to everything belongs to the open interval x minus epsilon to x plus epsilon for every epsilon, right? So x is here. So what is x by 2? X by 2 is somewhere here, right? Because the midpoint of 0 and x. So what I'm saying, so after certain stage, all the xk's are bigger than or equal to bigger than x by 2. Because by convergence, after certain stage, all the sequences lies in this interval. So in particular, it is which is bigger than x by 2. So this is always true. And even we can say, since x is positive, therefore x by 2 is positive. Therefore, after certain stage, all the xk's are positive. Okay. So after certain stage, all the xk's are positive, provided the x is positive. The limit is positive. Then after certain stage, the x sequence terms are positive, because after steady everything very close to x. Since x is positive, therefore we'll get a positive sequences. Okay, so for any doubt? Anyway, we can stop now. And the remaining things we will discuss in the next class. Thank you.